Right, it's a pleasure to be here today with the group at Sigmod. And I'm going to give you an overview of what we are doing here at Microsoft in the area of optimizing data platforms to be cloud native services that are easier to consume. And Carlo Curino, who's with me, will speak to a lot of the work we are doing to do machine learning to make all of this so much easier to operate. So the first generation of cloud essentially was making it easy to rent rather than buy hardware. And where earlier you would buy a collection of hardware, install it in your own data centers, install all the software from scratch, and go run it. In the cloud world, essentially, hardware was virtualized, deployed in large shared data centers. In fact, many data centers worldwide allowed for support for geo locating where you wanted your services to be, failover and the like. The operations, upgrades, dealing with backups, a lot of these were potentially automated. Most importantly, security was a large concern that the cloud vendors obviously took very seriously, invested literally billions in. And over time, security, which was seen as an inhibitor to coming to the cloud, became a reason why people moved to the cloud. And this allowed you to have essentially the ability to pay as you go. And oftentimes, the overall costs were lower. You had the ability to scale your workload up and down elastically. That was a big factor in that. And just in terms of the TCO of ownership, the simplification of a lot of the routine operations made things so much simpler, so much more cost effective. Well, that led to the cloud becoming something that's here to stay. But going forward, it's so much more. With the popularity of the cloud, virtually all software running in it, and most certainly the major database platforms, they're being built from the ground up to be cloud native, by which I mean to take full advantage of the strengths like elasticity that are uniquely available in the cloud, and at the same time to hide some of the larger latencies in the cloud, because storage is remote, right, and not co-located with compute. You really need to be thinking about the memory hierarchy, how to mask this latency. A second trend where you had a whole collection of siloed products in the old standard on-premises model, and where the first generation of cloud essentially offered the same services as silos in the cloud. Increasingly, we are seeing the ability, the opportunity to simplify by bringing together the core capabilities across what were hitherto distinct services, so that with a single sign-on, a customer can potentially do a whole slew of related things together in one place. And this means increased security, simplified operations across a spectrum of things you need to do, and just plain easier to get to what you want to do, as opposed to connect all the plumbing together. Lastly, modern data systems are complicated. DBAs have long been indispensable. They go in there and they tune all the knobs just so, right? In the cloud, there is this enormous potential to learn from all the instances that are running in the cloud and figure out how to tune these knobs automatically. And the promise here is you don't really need a DBA. The cloud operators, learning from the many instances they are operating, will operate your instance for you as well, right? And that's, of course, an ideal, and nonetheless, a realizable ideal and one that we're working towards. So today, we'll look into all of these in a little more detail. Let's begin with cloud native engines. In Azure, to be concrete, there are many examples. If you take the operational databases, key value stores, Azure Cosmos DB is a geo-replicated key value store. Right? Your data is instantly replicated to 3 locations worldwide. And you have Gremlin APIs, Cassandra APIs, Mongo APIs, SQL, a multi-model API instance over this underlying geo-replicated data. It's been built from the ground up to be cloud native. Another example, if you take analytics, right? We published a paper at SIGMOD describing the Polaris SQL query engine. That's part of the Synapse cloud native database system that brings together analytics, both warehouses and lakes, what we call the analytics continuum. I'll tell you more about it in just a bit. Finally, there's also SQL Server for OLTP applications, a scale-out version, cloud native in the cloud, again was described in a paper in SIGMOD 2019. And bottom line, every aspect was rethought, rebuilt to address the issues I talked about earlier. Take advantage of the elasticity. So if you look at the primary and the secondary compute nodes, you can add as many as you want, scale them up and down elastically. The underlying data, right, is accessible from the primary and the secondaries. And the latency that you need for high performance CRUD, transactional operations, it's provided by a very carefully thought out caching hierarchy, right? The underlying collection of page servers masks the latency that it would take to go continually for every change to the remote store, which is where you get the storage elasticity from. Again, my point here is not to get into the details of this architecture, but to make this broader point. Architectures in the cloud have to separate the data and transactional state from the compute. That is the essence of a cloud native architecture. I've given you examples here, but that's a common pattern you're seeing. Across the board, our workloads are being re-architected to be cloud native, whether it's NoSQL, whether it's OLTP, or whether it's analytics. And today we look at analytics in a little more detail. A related point, the distinctions between warehouses and data lakes or big data are disappearing. There's an analytics continuum. You get to keep your data in the form that's most appropriate, and you get to use the full spectrum of tools that have been developed in the worlds of big data and relational warehouses all together, because it's a spectrum of activities that's part of doing analytics. So rather than have multiple solutions, we think there's convergence happening here as well. And that brings me to the next theme, unified services. The cloud offers us a unique opportunity. Even when you have different services, whether they're different analytics services, whether they are an OLTP service side by side with an analytics service, whether it's analytics and higher level apps. The point is, all of these, their storage is sitting in cloud storage. Their compute is in cloud compute. And that brings them closer in an important sense to where if the software can understand how to bridge, there's no underlying thing preventing you from doing that in terms of the storage being in different physical systems, for example. You really have only your imagination blocking you from thinking about deeper integration so that people can do whatever they need to in common usage patterns end to end more easily. Let me speak to this. Our vision for analytics, based on what we have seen, literally hundreds, thousands of customers over the years, people want to do the full gamut, right? Spark queries, SQL queries, streaming analysis, machine learning, Power BI, Tableau kind of visualizations. Uh, they want to bring all these tools to bear to get insight out of their data. And what do I mean by data? The data that they have in their operational systems, the data in their lines of business. This could be SQL Server, it could be stores from other vendors, it could be NoSQL systems, it could in fact be file systems in which you have placed data for analysis, so-called big data or lake systems. Data is in a variety of physical repositories, and it comes from a variety of underlying types of systems. But nonetheless, for good analytic environments, a key criterion is you need to be able to look at all of the relevant data, a 360-degree view. So data variety, this variety in the sources, the variety in the data itself, your analytic tools need to be able to cover the whole gamut. You may want more than one tool. You want to be able to use all of them, have them compose with each other, understand each other's metadata and data formats. You want to make this as fluid as you can for the end user. And in doing this, when you have a separate siloed service for each query engine or for each data store, the plumbing, putting them together so that you have a secure environment, so that you can take it and address the concerns of governance, compliance, so that all of them are composed, tuned to give you good performance, scalability, to address availability, recovery. All of this, the more the silos you need to knit together, the complexity expands as the square of that number, right? And so deeply integrating across the whole stack, it's a journey. It'll take time, but that's inexorably the way it's all headed, because with that comes simplicity. As we observe the patterns, we can make the common patterns more easy, more seamless for end users. And this is the analytics continuum, right? How do we get there? In Microsoft, there's a concrete instantiation of what I just said. There's data from all these sources, operational databases, other sources. You want to be able to analyze all of it. You want to be able to govern all of it. And more on governance in just a minute. That's turning out to be an increasingly important pillar. And in Microsoft, for governance, we have a service called Purview. For analytics, we have something called Synapse. I'll tell you more about both in a moment. And these become the platform, the foundation upon which we build all kinds of applications, right? ERP applications, Office, and the canonical schemas behind those giant applications create shapes, common standard ways of thinking about important concepts like, say, customers, which, the notion of customer arises not only in Dynamics, but which is a CRM application suite, but in so many other application suites. Those common shapes, we build many, many apps to let you do, for example, insights over the data you have about your customers. You want to be able to leverage that app ecosystem over all your data that pertains to customers. We want to make that easy for you. So application data is stored as part of your data. The insights you get inform those applications. Making this easy attracts more people to build their applications against the common shapes. It's a virtuous cycle. It's an ecosystem you're creating, right? That's the vision we have. And that's the role we see for analytics and governance along with operational stores, right? Let's actually take a look at that in a bit more depth. We're all familiar with OLTP and analytics. In fact, the database community has had specialized benchmarks for many, many decades, right? The TPCC, TPCDS, TPCH benchmarks are familiar to all of you. So these two pillars, operational data, analytics, are well known. But governance, grant revoke statements for RBAC as an example, have long been features of database systems. Now they are breaking out of a database. Governance is becoming an independent pillar of its own, right? Why? Take GDPR and other compliance regulations. You need to be able to ensure that all your data is used in ways that conform to the requirements, not just the data in this instance of SQL Server or that instance of Oracle or that HDFS file system, all your data. Likewise, when you think of people who have data spread across many locations or managed by many groups within a company, nonetheless, you need to be able to set some policies that span the whole, your entire data estate. How? Unless you have something that's a single pane of glass allowing you to author your governance policies, to look at all the data you have, to enforce these in a more unified way. How? We don't have the tools. And that's what's emerging as we speak. And that third pillar, we are working towards that. Our suite is called Purview. Again, I won't say a whole lot about that, but that's something to keep in mind because it has to be deeply integrated with everything related to your data, including the operational and the analytic estates. Okay. Furthermore, these are not silos in themselves. If you take data that's in the operational stores, often you want that available for analysis in your analytics environment in near real time. Operational analytics is increasingly important, right? So operational data has to be managed in its own distinct way because the usage, the workload is so different from analytics. But you want to make that data readily available for analysis. So we have a feature called Synapse Link to address this. Governance. As I said earlier, you want to discover what data you have. You want to discover everything you can about it. Its schema, the details of the data, the semantics, and as much richness as you can glean. Lineage, where did that data come from, right? You have to track that lineage through all subsequent use. Ability to share the data across organizations even. All of this together with the governance policies, ABAC, and so on. That's something that touches every piece of your data platforms, right? Okay, we learned all of these lessons beginning with our own internal journey at Microsoft. If you look at our internal lake, right, which is used by virtually every part of Microsoft, the amount of data, the number of developers, the number of teams involved, truly it's staggering. And when GDPR came along, we had to do everything I just mentioned in the context of this very real complex environment. And over the course of doing this, we had one more principle that we were trying to follow. Whatever we did internally, we needed to get it to be in a place where ultimately we could offer it as an Azure service. Microsoft believes very much in drinking our own wine. Okay, 1P first-party solutions should also apply to 3P or third-party customers. So already all of the data here runs in the ADLS service. All of the analytics we are doing in our internal lake is migrating to Synapse. It's deeply aligned with Hadoop. So this illustrates kind of how we are approaching the challenge. Let's take a look at Synapse itself. The analytics world on Azure had several services, right? A Hadoop service, a data warehouse, a data factory, which was a data movement and orchestration service, a log analytics service, streaming, cognitive services. And customers could enter through any one of these services and try to use them as standalone services. This got to be really, really difficult for people who used multiple services. So Today, the core capabilities from these services are all bundled. They're accessible in one integrated environment where the services understand each other's metadata, data formats, and whether you use a notebook or a studio environment or a Power BI dashboard, you still have access to all the underlying engines, Spark or SQL or log analytics, all the underlying data, whether it's stored in files and folders or managed data tables, right? That's the Synapse offer. And if you look at this picture, it also highlights a couple of other points. One, we are actually very committed to open interfaces and interop with even things in the broader Azure ecosystem that have not already been deeply integrated into Synapse, right? The other point I want to make, I want to dig a little deeper into how you store data, this continuum that I mentioned. You'll have heard terms like lakehouse, warehouse. What usually means is a lakehouse, you store data in files. And if you want to modify your tables, then you have lazy log structured schemes, Delta Lake, Iceberg, Updatable Parquet, Hudi, right? In a warehouse, you're optimized for data that's transactionally optimized, transactionally updated, and in fact, updated fairly often, right? But those really expect the storage part, right, has different characteristics whether you, as you go from left to right on the spectrum. But we think there is no reason why you shouldn't be able to take the query engines, the analysis tools that you use on files and apply them to data that's stored in transactional tables, or to take SQL, which primarily developed in the context of transactionally managed databases, and bring it to bear on data in the full spectrum that you see on this picture. And that orthogonal separation of the different engines from this full spectrum of the underlying data, that's core to the Synapse architecture and design philosophy. Speaking of operational analytics, what I showed on the previous picture represented the continuum of analytics data. What about data in an operational store, such as, say, Cosmos DB, right? That data is in a different place, and it's going to remain in a different place because it's optimized for transactional CRUD. You know, go change the amount of money stored in this account, which is very different from give me the average amount stored in all accounts. And so those two systems are going to be different. But what if you want to do analysis over the data in a transactional store? What we essentially support with Link is a way to create and maintain a columnar version in the analytics hub in Synapse of data in an external operational store by looking at the change feed, continually bringing it over and maintaining it in a columnar form incrementally, right? Think of it as creating an index in Synapse of data in an external operational store. This is completely system managed near real time. That's how we try to make it easy to do analysis over all your data. Finally, let me tie together the importance of governance in this environment. Simply knowing what data you have across this entire real estate, whether it's on-prem, whether it's in one of several public clouds, whether it's in a file system, whether it's in an operational store, whether it's in a data warehouse, right? It's non-trivial and incredibly valuable. Being able to do more, learn whether some of the data is personally identifiable or highly sensitive, to be able to encrypt and keep it encrypted as it travels through this ecosystem, to be able to enforce ABAC controls. These are all things that we need to be able to do and can't always do. As data moves, keep track of lineage, how is it evolving? Let me just give you one end-to-end picture to illustrate how incredibly empowering this can be and what a big gap it is today. This is a complicated slide, but bear with me. What it shows you is the process of training a model. This is what you see in the top rectangle. And training is done in an environment of choice for a data scientist. This could be PyTorch. It could be one of several popular environments for training ML models. When you do that, you typically then deploy these models someplace where you want to use them. So for example, it could be a fraud detection model is deployed in a place where requests are made to evaluate the requests and classify them as fraud or not, right? This could be in a database system. It could be in an edge device. It could be in many, many places. When you use that model to make a decision, all kinds of questions arise. Was it fair? Was that decision fair? And in turn, that means, was your model fair? To answer that, you need to know what kind of model was it? How was it trained? On what data was it trained? Was that data representative or somehow biased, right? And you need to have full lineage. The model itself, the model provenance, the deployment, who deployed when, where, which particular model, the deployment provenance, when it was scored, who made that decision, the details, the scoring provenance, and putting it all together using lots of techniques that researchers in fair use are working on. You can actually bring some insight to bear on whether the decision was fair or whether there's potential for bias, so you can then go dig deeper. But all of this model provenance, this is part of the lineage of the data. Lineage is fairly complex, as you can see from this example. So when I said we need to track lineage, this is what illustrates both the power and the complexity. The lineage in moving data, the lineage in running queries over it, the lineage in building models, deploying models, scoring models, everything has to be tracked. And then you can put this together in useful ways to inform the conclusions that you draw from your data, right? And this full life cycle has to be governed. Who's allowed to train? Who's allowed to deploy a certain model for a given purpose? Who's allowed to use the deployed models for what purpose, right? What data can be used for different kinds of training? When is it allowed to be seen by whom, right? For what purpose? All of these, the bar for the level of granularity and types of controls that people require keeps going up and up and up, right? So the increasing richness of governance tasks and the fact that they now span data in multiple repositories and the use of multiple engines makes this a grand challenge problem for us and our community. And all of these steps, their richness, their complexity also makes them a very fertile area to bring tuning, machine learning to bear on streamlining, on simplifying. So thank you. With that, I'll turn this over to Carlo, who will talk in more depth about how we are using machine learning for systems, for simplification, for optimization across the spectrum of the kinds of services I've talked about today. Thank you, Carlo.
Thank you, Raghu, and thank you everyone to listen to our presentation. So let me go back to Cloud 1.0 and one of the issues with it. So as Raghu described, there's already a lot of good things that come with Cloud 1.0, right? We have simplified incredibly the sort of maintenance and management of systems, things like updates or backups or disaster recovery kind of issues, hardware maintenance are all taken care of by the cloud. However, there is a only partially fulfilled promise, right? When it comes to data management, the mantra, the belief was, hey, when you move to the cloud, you're not going to need a DBA anymore. Well, as I said, some of it is true, But there are other things that DBA does, right? The database administrator was working on choosing which query can run on which databases, not to overload a database, or determining indexing or tuning parameters of the system, selecting what views should be materialized to really get the workload to run very efficiently and with very, very good performance. So this is today still not completely true in Cloud 1.0. And this is what we aim to achieve by going beyond Cloud 1.0. In particular, one unique angle in the cloud is that now the people that are building the software can now operate it as well. And so we collect an incredibly rich telemetry about the systems we are operating. Also, there's been a fantastic evolution of machine learning and data science. It's now becoming very powerful, and tools are readily available. And of course, we can throw a bunch of new research and really go beyond Cloud 1.0. So this is to say, we're not going to solve this problem by just throwing a lot of database administrator behind the scene. That would be impractical on one side, and also they don't have access to your data, so privacy issues there. But really, it's all about automating. It's all about leveraging machine learning, leveraging great telemetry to sort of close the loop and automating as much of the problem as possible. But let me try to be a little concrete about this. Let's take one specific example. Let's imagine you get a query, maybe an analytical query, something like a Spark query or a T-SQL query running on a data warehouse, and you want to run it in the cloud on top of one of these systems. And let's see all the things that need to happen end-to-end, from the query being inputted all the way down to the hardware, everything that need to be tuned for this query to really run as good as it could. So first of all, you're typically requested to choose what is right kind of VMs to run on, and even sometimes how many containers you want to run on. This choice could be static or dynamic. You can leverage auto-scaling, but it's fundamentally a very difficult question. To put this to the test, we selected a group of 7 really expert big data engineers and PhDs with, in research, right? So there's a group of people that have like at least 10 years of experience in the field, and we gave them a super simplified version of the problem. We took 2 queries from the Big Bench workload, query 1 and query 3. We took 2 configurations from Azure clusters, same set of VMs, just 2 different kinds of VM, and we asked them to estimate how fast each query would run on each one of the configuration. Well, it turns out these users were way off, from 5x overestimating to 20x underestimating the actual runtime of the queries. And you could tell us, yeah, but the exact estimate doesn't matter. What matters is the ordering. Well, 6 out of 7 users actually assign the ordering wrong. So we're not able to guess which query would run better on which hardware. And this is very problematic. So these were not only were expert, but we gave them a really simplified use case, only a couple of queries. Not only that, we gave them access to the query plans and even the cardinalities of all the actual cardinalities of all of the tuple flowing through the query plan. So even in a super simplified use case with expert user, it's very hard to make a decision. This tells us that this is definitely a decision that should not be in the hands of the user. We should automate this. Other difficult decisions that we see happening all the time are ways to influence the query optimization. So in our internal big data infrastructure, we see very often very expert user tweaking and giving hints to the optimizer to inform the optimizer about skewing their data, or whether certain cardinalities, for example, going through a UDF, how many tuples will make it through, or tweaking the cost models, or even influencing the search space by enabling or disabling certain physical operators, certain implementation of a join, for example. All of this is possible and really makes a big difference in some cases for the queries, but again, quite sophisticated for normal users. When it comes for actually the query execution, again, huge number of possibilities, even just on the physical data layout space, choosing how to represent the data, partitioning, indexing, sorting. All of these mechanisms are available, but they're quite hard to figure out. Also, caching strategies. Once we're in the cloud, as Raghu mentioned, now we have a much richer set of hardware available. We have remote store, which could be caching data there. We could cache data locally in SSDs or in main memory. We can cache in main memory of another machine that is RDMA reachable from my node. And what are the right policies? What to cache, where to cache, alone an incredibly rich space of optimizations. Now, all of the things I mentioned are really hard, but they are more or less accessible for a user. Now, there's another series of optimization that are even deeper into the system, that are even harder to achieve by the individual user. For example, pipeline efficiencies, things like that a DBA would normally do in an on-prem settings, like looking at the entire query workload and defining materialized views. that reduce the redundant computations. These are very difficult things to achieve. And a user in the cloud might not even have access to this because they might not be able to see the queries from another user that belongs to the same organization. We've also learned that by observing in our internal big data infrastructure, by observing the entire pipelines and the start time and end time of every job, we could, and the data dependencies through all of the governance and provenance work that Raghu was describing, we could infer deadlines and even the importance of jobs. And this would be an incredibly useful piece of information to affect scheduling. Again, not something easy to do for users. Finally, the query hits the actual cluster and start running. Well, down there, we still have a lot of tuning configuration and tuning opportunities. For example, even just simply how many tasks do we run on every node? Running too many would sort of choke the resources of the system and not run really fast. Running too few will increase the cost too high for the user. Similarly, we can decide to run on dedicated VMs or harvested resources, like leveraging resources where on machines where the resources are already assigned but not fully used. And so we can harvest cycles there, again, making it very cheap as an overall cost of ownership. And finally, we want to schedule management operation, things like backups or vacuuming of a database or power cycling of a machine to install a new operating system. And this is not just the end of this, right? Once we go down, since we own the system, we have built SQL Server. We could in principle go down all the way to look at things like typically constant in the system, like the wait time for a spin log, and look at your query workload and tune SQL Server, transform and recompile SQL Server to run absolutely optimally for this one specific use case. So I believe that kind of get the point, right? There's a lot of opportunity for tuning, and you might imagine that I'm giving you this big laundry list just to tell you how big is the space and how much needs to be done, and this is definitely true, but there is more to it. There's a tons of work that we've already done in this space. These are just Microsoft publications, at least the one I know of. There are kind of recent in this space. There are 3 publications just in this year. Sigmund, and the honorable mention of the Sigmund Industrial Track is in fact one of the piece of work in this space. So huge amount of effort that is happening in Microsoft, right? This is a real big thing, and this is just Microsoft. There's tons more work happening outside, and even more important, I would say, this is not just an academic exercise. This is not just interesting research papers that we can write in this space. Much of this work is actually landing in all the product that Raghu described. Now, I don't have time to go over all of them and show all of the examples, but I'm just going to pick the Cosmos internal big data infrastructure and just give you a highlight of some of the big wins and sort of dollar numbers that we saved in that context. The reason I'm picking Cosmos internal is, as Raghu mentioned, this is our sort of internal gym, right? This is how we start all of the technologies and we bring them to the third party all the time. So Cosmos is a bit more mature, it's a little easier for us to operate on. So here's some examples, right? We operate a big data infrastructure. The scheduling is based on Yarn, and tuning certain internal parameters of Yarn can lead to a $19 million, as led actually to a $19 million cost savings for the internal big data infrastructure. Similar kind of technology combined with very cool power capping technology from MSR, we were able to reduce the power bill, the cost, the amount of electricity that is sent to this, that is provisioned for these clusters, and saving about $30 million a year in consumption. Plus, this allows us to actually squeeze more servers and other workloads in the same data center. So we even save constructions of an expansion of a data center. As I mentioned, we can also look at sort of harvest VM versus dedicated VMs. This appears to, we have projections that this will give us about $17 million a year gains. Things like computational reuse, our Cloud Views project is on track to deliver about $40 million a year worth of savings. And we have in production the first, what I believe is the first production use of learning cardinality, so a machine learning based cardinality estimation. And this seems to be reducing by about 6% the cost for all of the job, in average for all of the job that where we can apply it. So overall, lots of significant wins. These are just a few samples from the Cosmos ones, many more across the entire fleet. Now, as you can imagine, this laundry list of things that we can do and the number of different engines that Raghu described create a really huge space. Now, going about it by simply sort of inventing and building a new solution for each one of these is incredibly costly and is, just not efficient from an engineering perspective. So really the name of the game to scale, like the next level for this, is to come together with a shared infrastructure. We're now in the process of taking all of these good examples, all of the things we have learned over the years, and work more and more and more towards a single unified kind of way of tackling this kind of machine learning for systems kind of work for cloud tuning. And let's go over this sort of idea of a unified tuning infrastructure. So taking the usual query, I've broken down a query processing stack in very, very simple steps like optimizer, scheduler, runtime, and cluster. The most important thing in the stack itself is at first to collect very good instrumentation. Collect informations from all the way from the query. So what is the plan that is being used in the query? The behavior of task on machines, so runtime statistics, information about CPU utilization and consumption of individual tasks, overall load on the machines, potential signals about noisy neighbors, like everything we can possibly collect in terms of the entire end-to-end behavior of all of our queries and all of our clusters. This is a huge amount of information, right? Just in the Cosmos internal infrastructure, this amounts to something in the ballpark of 10 to 15 petabytes per month. Now you can imagine we can't just take all of this and just plop it and just run a big ML DNN on top of it, right? There's a very, very key step, which is sort of workload representation, right? You can imagine this as sort of like a data processing step, but it's really about designing clever generic ways of capturing all of these workloads and modeling very, very carefully. These decisions are really fundamental to then enable a generic way of constructing specific optimization and models. So this step number 3, which is workload analysis, is where all of the modeling, the algorithmics, the optimizations comes in. Different examples, like the one I've done in a couple of slides ago, will obviously require different models and different algorithms. But ideally, they all are based on pretty much the same set of data, the same workload representation. One of the things we found very interesting is instead of going after Uber models that can represent the entire workload, the entire cluster, all of our users, we found it very successful to go after what I would describe as micro models. So models that can describe a local behavior very, very well. As an example, in terms of learning cardinalities, instead of predicting all of the cardinalities in the world in a single model, we could go after the behavior of a certain couple of tables and how do they join and how filters will produce cardinalities or not. If we can build a micro model for that, and we make the retrieval of the micro model and the inference of the micro model really efficient, then we can be very, very specific, right? And deliver great value there. And then generalize with more models that are more abstracted. So that comes to the next step that is very important, is the serving of the models and the serving of all the insights that we have gained in the step up to this point. Again, this could be a scalability issue, right? We might have tens of thousands, hundreds of thousands, or millions of models that can affect different behavior for different users or different queries or different time of the day. And so being able to quickly retrieve the right models and quickly do inference on them is actually really important and a really key element of our infrastructure. And finally, we want to close the feedback loop. We want to go inside the engine and modify some of the component so that they can make use of this modeling and these insights. As an example, again, using learning cardinalities, the optimizer itself will call into the Stats and Insights service, download the right micro models, and execute inference on them so they can predict what would be the number of tuples that makes a certain operators through the stack. So this is a very generic solution. Let me describe it, at a high level. What are the different things that we can tune, right? We can tune anything from the default configuration parameters, or have them dynamic, resource allocations, the estimates of an optimizer, physical designs, computational reuse. All of these are example, right? Like we've been going through before. The key takeaway from these slides is the learning and decisions could happen both online and offline, all the way from developer time to the runtime of a query and anything in between. Most typically, we've found that learning offline, it's quite useful for us. It's useful because it allows us to create a fair bit of confidence around what the models have learned and what would they do. But the decisions tend to be online. Some of them are offline, but tend to be otherwise online. Now, this is a current snapshot of where things are today. I don't believe this is going to be always the case. I believe more and more we're going to move towards a more dynamic, online, automated way of doing things, but it's a long journey, right? Creating the awareness and the understanding and the right tools and the right monitoring and guardrails to deploy machine learning in production. It's a big, big journey. And this is where we are in the journey so far. Now, I would like to go over all of the example and share a lot of the excitement in all of the various pieces, but I don't have the time to do this. What I can do though is to jump into one little simple example. We're gonna grab a simple case like setting the default configuration parameters, but I'm gonna describe you a generic infrastructure we're building to do this kind of work. Interestingly, this is also open source, so you can get to use it yourself. The project is called MLOS, or Machine Learning Optimized Systems, and what it is a developer toolbox that is designed to democratize the use of data science for system optimization or for software performance engineering if you want. The project is open source. You can find it at Microsoft GitHub.io/MLOS. And you can find sort of notebooks and experiences. We use this for a class in collaboration with University of Wisconsin. So there's a good initial resources for you to play with. Let's see what's the motivation of MLOS. This is a change, a commit log of a change of a specific parameters, one line of code change in SQL Server. Now I'll tell you this was a very expensive single line of code change. What happened is that some of our customer had some performance bugs and start complaining that SQL Server was not running well in their use case. So some engineers start running a lot of experiment, obtain from the customer some way of kind of replicated the workload, and start running as many tests and as many experiments as possible. Turns out the issue was a spin lock consuming too much resources, and that was due to a hash function that was using the spin lock was kind of skewed in the way it was mapping the data. So what we find in the log, in the comments in the log, there is a reasonably cryptic commit log that says 53 is a prime number and should work better to fix the performance issue of our customer. Wow, so now we went from one magic constant to another magic constant that happened to be prime. What is the issue with this? So this is a traditional software performance engineering, right? Edit the code, compile the code, deploy the code, run some benchmark, and iterate. So this is really bad in many ways. One, is very slow. This is a single line of code change that took a long time to get right. Two, is poorly documented. All we know is that now SQL Server has 53 in the code, and not 50. And 53 seems to be working better. This is also reasonably brittle. For this customer that we tested and for our reference benchmarks, 53 works well. But who knows if in the meantime we broke the behavior for someone else. It's also reasonably exclusive, right? Setting up this benchmarking infrastructure is quite complicated, it's quite clumsy, quite cumbersome. And it's very repeated, right? As we shift to different hardware, we'll have to tune some of these parameters again. If different workloads come in, this will happen again. So we want to make all of this better and more systematic. And if you notice some of this behavior of like running an experiment and evolving and changing and etc., they are very data science in nature. A lot of the Bayesian optimization style of data science very much tries to do the same, right? Tuning parameters. So what we try to do is really giving system developer access to the tools that are normally very exclusive to machine learning expert in the data science world. So we're trying to make it easy to plug in a data science experience with your software development experience. So first of all, how we do this? Well, we try to introduce annotations and leverage code generation so that instead of setting the constants by hand in the code, like 53, we now have a way of register a parameter and says, this is a constant that we would like to auto-tune. Next, we want to pair this up with performance unit test. Ideally, the smallest possible unit that can verify what is the correct value, but also associated with very, very generic all up end-to-end benchmarks. MLOS here helps you a little bit beside the code generation because it gives you the ability to capture a lot of the hardware and software metrics, NOS metrics automatically. So when we measure something, we will have the runtime of your query as well as a lot of observations, what is happening, like, how many cache hits were happening or how many NUMA channel crossings, so on and so forth. This helps us understand what's happening inside the code itself. Next, we very systematically externalize all of these observation in an external agent. This is because we don't want to have new, messy, complicated testware kind of code inside the core of our system, say SQL Server. We want to park this on an external agent and be able to be more free in the way we experiment in this space. Next, we leverage Bayesian optimization. This is a very efficient way of searching a large parameter space. I'm sure that over time we will experiment with other things, but this is what we have in the system right now, and it's serving us pretty well. And finally, we bake all around it a very nice, rich data science experience, including visualizations, interactive, notebook style ways of interacting with the entire system. It turns out this is incredibly important because once we find a good optimal new value, the immediate next question from the engineer is, why does this work? What is happening? Why is it working better? Why is it looking like this? So this is just give you the intuition on the MLOS project. Next, let me just wrap up with some lessons learned. So in general, you like telemetry. No matter who you are, no matter what's the system, there's always something more we can capture, something more we can collect that will give us a better insight of what's happening in the system. Next, it is all about the infrastructure. The specific modeling exercise is fun, is interesting, is cool. But a lot of the work, about 90% of the work, is really all of this like end-to-end loop that I was describing, not just the little modeling piece in the middle. Third, insights matter more than automation. While automation is our eventual goal, what we notice is that the moment we build the right infrastructure, the moment we have the right telemetry, there's a lot of great insights we gain to understand better what the workload is, what the system is doing on top of different hardware. And there's a great deal of engineering that is happening because we have these insights beyond the specific task of automation that we're after. So insights definitely going to be super important. Next, you cannot afford to do this for every single engine, for every single app. As I described, the list of like 20 or 30 papers that I have there, if we were to do each one of those for each one of the like 10, 15 engines that Raghu described, that would be a huge, huge engineering effort. So it's all about sort of factoring out the common components. And again, a lot of that is part of the infrastructure parts, and really focusing on those. And we're even being successful at applying the same algorithm across different engines because we're sharing infrastructure now. And finally, I will allow you to use a DNN once you can show me that you can be trusted with a linear regression. This is obviously a joke, but it's a way of saying fancy machine learning models are not really the answer, right? We should start from simple model. This is one because very, very often they're sufficient. Right? Sometimes we don't even need machine learning. It's a simple threshold. Will get us, 99% of the way there. And second of all, because in general, we want a very explainable machine learning. And so far, linear classical machine learning typically is more explainable and more understandable for the software engineering people that we will be working with and deploy these kind of fancy ML solutions in the system that they own. So in conclusion, telemetry comes before infrastructure empowered to get you insights. Insights will lead you to the right automation. And then you can use fancy model or even fancier model, but just little by little, just using the simplest one possible. So in conclusion, we started with the question, what's beyond the clouds? Well, we believe this is going to be a very sunny future where we're going to use all of these machine learning and data science that I described to tune these fantastic cloud native engines that we built that you can consume in fantastically unified services. And with this, I conclude, and I'm available for questions. Thank you.